Okay, so now we're going to take a look to see what we can use to gauge or to predict the strength of an acid. And we're going to now take a look at the structure and how that influences uh, strength of an acid. So molecular structure and acid strength. Now, first of all, let's define what makes an acid strong. And the strength of any particular acid can be measured by its tendency to ionize, right? And when it ionizes, it's able then to produce H plus ions, right? If you remember from the Bronsted definition, acid is something that donates protons. So if something is able to ionize, in other words, to produce ions, have that H plus there, and if it's able to do that relatively easily, then it's considered a strong acid. So there are two main factors that can influence the ionization and as a result influence the strength of an acid. The first is the strength of the HX bond. And X here, by the way, is just an anion. Um, that's just the way we generalize what the other part of the acid molecule is. X could be a halogen, it can be a polyatomic, doesn't really matter. The strength of the bond between the H and that other part of it can influence ionization. And in addition, the polarity of that HX bond also influences the tendency to ionize. All right, so we'll just summarize what those trends are, and we'll take a look at an example. So you think about having a bond between the H and the X being a strong bond. Okay, so if this bond here, I like it in yellow, if it's strong, that means it's very hard to break. And if it's very hard to break, this process up here is not going to happen. And if this doesn't happen, it's not producing a lot of H plus, which means that acid then is going to be weak. So we can summarize that and we can say the stronger that HX bond is, the stronger the bond, but it's harder to produce ions, which means the weaker. Okay, and then that's because not a lot of H plus produced. Okay, that's the first thing. So the stronger that HX bond is, the weaker the acid is. The polarity then of the HX bond also influences ionization. So if we have a big difference in polarity between the H and the X. In other words, if the X, for example, if it's highly electronegative, because the electronegativity of the H doesn't change, right? So if X becomes more electronegative, that means it's pulling on these electrons that are being shared more strongly. Okay, so it's pulling on those electrons towards itself more strongly. And what that leads to then is that leads to separation of charge. It doesn't cause this fall off essentially much more easier. Will cause the H plus to fall off more easier, and as a result, more H plus is going to be generated. So we can summarize that and we can then say the more polar the bond, and the stronger the acid is going to be. Okay, and that's because lots of H plus will be produced. Right, so again, if the X, whatever X is, if it's very highly electronegative, it is pulling on these electrons towards itself, okay, and separating, causing that separation of charge to happen much more easier than if they had similar electronegativities between the X and the H. So we'll take a look at a couple of specific examples of where those factors show up in the acid strength. And we'll take a look, first of all, at hydrohalic acids. The hydrohalic acids follow the same general formula, HX, but this is specific now where X is going to be a halogen. Okay, so things like fluorine, the group 7 elements, fluorine, chlorine, bromine, and iodine would be the most common ones that we're going to see. And the biggest factor that we're going to see here that influences the strength of the acid is the strength of the bond itself, right? And the way that we look and we judge the strength of the bond is by looking at the bond enthalpy, right? Which are tabulated here for the different H or H to the halogen bonds. So the bond enthalpy, right, is the way that we quantify that relationship. So the higher the bond enthalpy, the stronger the bond. Right, that's the amount of energy needed to break that bond. So for example, HF requires a lot more energy to break it. So it's a very, very strong bond, which means it's not going to break very easily, which means it's not going to produce a lot of H plus, which makes it a weak acid. If you compare that to HI, hydroiodic acid, the bond enthalpy there is almost half. So it's a weaker bond, much weaker than a HF bond, which means it's easier to break that bond. And if it's easier to break it, we're going to produce a lot of H plus, which would then make it a strong acid. So out of all the hydrohalic acids, only the HF is considered weak. All the other ones are strong because of their fairly high, I'm sorry, fairly low bond enthalpies, right? So for hydrohalic acids, the bond strength factor is the factor that dominates and influences the strength of the acid more than the polarity of the bond. The other main types of acids that we'll see are the oxo acids. Oxo acids, as the name suggests, contain hydrogen, they contain oxygen, most importantly, and then they also contain a non-metal atom that is usually in the middle, or a central non-metal atom. And the general trend here that we're going to see is that if that central atom, the central non-metal atom, is electronegative, or has a high oxidation state, then that acid is going to be strong. Okay, so in the case of the examples, or the reasons why that would happen, again, if we consider the characteristics of these different things here, if that central atom is electronegative, or it has a high oxidation state, what that means is that it will attract electrons. Okay, so that central atom will attract electrons to itself. And as a result, it will cause that OH bond to be more polar. And if it does that, well, then we have a separation of charge. It's easier now, for example, that H to be lost in the examples shown. And if it's easier for the H plus to be lost, or donated, then that in summary then would mean that it's a stronger acid, as the acids do, they donate H pluses. So we're looking here for that central nonmetal atom. Is it very electronegative? Does it have a high oxidation state? That would make it a stronger acid than if the opposite were true. So here are some examples of oxoacids that you've seen or that you've used maybe previously. So carbonic acid, which has the chemical formula H2CO3. We have phosphoric acid over here. This is 3, PO4, sulfuric acid, H2SO4, nitric acid, HNO3, and then the less common ones, things like nitrous acid, which would be HNO2, we have phosphorus acid, which would be H3, PO3. All of these fit the criteria for oxo acids, right? They're hydrogens, they have oxygens in them, and then a central non-metal atom, carbon, nitrogen, or phosphorus, and the ones, or sulfur as well, the ones in the bottom. So when we compare oxo acid strength, it's best to compare sort of apples to apples or oranges to oranges, if you will. So we're going to divide them into two general groups. The first group is oxo acids that have different central atoms that are from the same group of the table, the periodic table, and that also have the same oxidation number. Okay, so for example, we have the one on the left here. So our central atom there is chlorine. You have 3 oxygens around it, along with the H on the left side. And on the right, you have bromine as the central non-metal atom, 3 oxygens around it, H to the left. Chlorine and bromine are in the same group, they're in the halogen group. And the difference between them then obviously is the Cl. Yeah, everything else is the same oxidation number, same group of the periodic table. The difference between them is the electronegativities, right? So Cl is more electronegative. Chlorine is more electronegative than the Br. It's lower down in a group. Remember, as you go down a group, the elements become less electronegative. So if this chlorine here is more electronegative, what it does is it pulls on these electrons towards itself. It pulls on these shared electrons towards itself. It makes the OH bond more polar. As a result, it's easier to lose or donate that H plus, right? That's the reasoning behind this difference, where you have different central atoms from the same period, the same group of the periodic table, but the same oxidation numbers. We look at the electronegativity differences to predict their relative strengths. So here the HClO3 is going to be a stronger acid. And then the HbRO3 is going to be the second group is oxo acids having the same central atom, but different numbers of oxygens, and as a result, different oxidation states as well. So we have here a good comparison to make. We have hypochlorous acid with an HClO. We have chlorous acid, which is HClO2. We have chloric acid, HClO3, and prochloric acid, HClO4. So the differences here is, well, the difference is the number of oxygens in each of these, and the resulting change in the oxidation state for the central chlorine atom in each of these as well. So what we're going to see here, the general trend is as the number of attached oxygen atoms increase, the number of oxygen atoms increases, the oxidation number of the central atom also increases. The oxidation number, abbreviated as ON, the central atom also increases, and as a result, right, if that oxidation number increases, it's more positive as it goes from top left to lower right. Again, it's going to attract those electrons to itself more closely, and again, it'll make that OH bond more polar, leading to that H plus being lost more easily in the case of the prochloric acid compared to the hypochlorous acid, where this OH bond is not as polar. Right, so as the number of attached oxygen atoms increases, oxidation number of the central atom goes up, and that leads to a stronger acid. So out of these 4, the chloric acid is the strongest, and then the hypochlorous acid is the delete this. If you are unfamiliar with, or if you forgot how to calculate oxidation numbers, you need to go back and review that. That's something that you would need to quickly determine if you use oxidation numbers if you're rusty. And that's a Jam Chem 1 technique that we learned a long time ago. So another really big category of acids that we really don't touch a whole lot in Gen Chem, but you will see a lot of this in organic chemistry. It's called carboxylic acids, or CA. We often abbreviate these as. And these are not inorganic acids like the ones we've seen before. These are organic acids. See them a lot in organic chemistry. And the general formula for carboxylic acid is R C double bond O and OH, or sometimes this is just abbreviated as RCOOH. R here represents the rest of the molecule, or the remaining part of the molecule. Really the reactive part of it, what makes it an acid, is the part here, the COOH. Right, and specifically now we know we could predict which of these, or which part of it is the actual part that's going to lose that H plus. That's obviously going to be that H. That's the acidic hydrogen in a carboxylic acid. Now, when this loses an H plus, we end up, this is your acid, we end up with a conjugate base. Okay, and the conjugate base is going to be RCO with a minus charge on it. So that's a conjugate base. And this all obviously is an anion as well. And because now we have this double bond here with our lone pairs remaining on each of these, this can actually exist in another Lewis structure where the double bond is on the right side, like so. Right, and you probably remember this from Gen Chem 1. This is called resonance structures. And what this leads to is actually stabilization of the conjugate base. Right, so when you have this anion being formed, and you have the possibility of having resonance structures, that means that the electrons can be delocalized. So for instance, this pair of electrons here are actually, they don't really belong to that place. They're actually spread over the entire molecule, this section of the molecule. So we say that it's delocalized, and that leads to stabilization of the anion. If the anion is stable, that means that it's easier for the acid to lose that H plus because it wants to go to the more stable thing, right? So what this means then, a more stable anion going from a acid. So if that conjugate base can be represented by more than one resonance structure, that means that the anion, that conjugate base, is resonance stabilized. It's very, very stable, which means that it wants to lose the H plus. The acid wants to lose the H plus to become that stable conjugate base, or the anion, which means that acid then is going to be stronger than if that wasn't the case. So in your carboxylic acids, that strength of different carboxylic acids now, because all of them are going to have this carboxylic acid part in yellow, right? That's going to be common to all of them. So the conjugate base is going to be stabilized by resonance delocalization. What makes carboxylic acids different from each other? Well, the acid strength is going to depend on the nature of that R group. So the R groups in acetic acid, for example, is this entire thing here. And the R group in chloroacetic acid is this thing here. So if you look at the difference between them, right, the difference between acetic and chloroacetic acid is the chlorine, right? Rather than chloroacetic, it's not in acetic. We just have 3 H's around the carbon. We draw these, right? So the difference there is the Cl. Now, that Cl is more electronegative than even the C or the H's that it's connected to or that are nearby. And as a result, that electronegative chlorine atom is able to pull electron density towards that R group And if it's able to pull electron density towards the R group, it is then again going to make that OH bond more polar. This bond here. Here it's going to be less polar. And if it's more polar, it's easier to lose that H plus. The other thing here is that once we form that conjugate base, those electrons that are being delocalized, they can now delocalize over much more of the molecule because they're being pulled towards the Cl. They're not being pulled towards the H's in acetic acid. If those electrons can spread out more over the entire molecule, that makes that conjugate base even more stable, which means the acid then wants even more to get rid of that H plus, which would make it a stronger acid as well. So out of those two, the chloroacetic acid would be the stronger of the two. Okay, so the Cl helps to stabilize or help to further stabilize the conjugate base. Okay, and that means then that the acid is going to be stronger. This is something, the last couple of things we talked about here are things that you're going to see a lot in organic chemistry when you have to try to predict and rationalize the differences in strengths of not just acids but bases as well. So we're getting a taste of it here in general chemistry.